afternoon session. Welcome, madam. Now the
Thank you
session
so
is
much.
yours. Yeah.
Thank you so much
Thank you, madam.
for your invitation.
Thank you.
I'm so happy.
Thank you.
And as you said, I'm experienced in not only industrial engineering, but also according to my PhD in computer engineering department. And it is very nice to meet some professors in AI and robotic systems. And I experienced this field. And right now I'm a lot of conference. I had a lot of conferences, invited talk as talker, and so much articles and other stuff. It's very new and hot topic when we are talking about explainable AI. And I want to introduce what is explainable AI and how this affects our research field. And I prepared a PowerPoint presentation, and show you let me show you this. First of all, I have to share my screen, and just hold on a sec, please. Do you see the screen?
Yes, madam. Yes, madam.
Okay then. And hello everyone. I'm Nilgün Şengöz, Dr. Nilgün Şengöz. I completed my undergraduate and graduate education in industrial engineering department, and I did my PhD on explainable artificial intelligence and deep learning in computer engineering. Now I will give you information about the hot topic, which is important in medical research field and the other research fields, explainable artificial intelligence and deep learning related to my research and my thesis.
Madam, you are.
By the way, if you want to this presentation, I can share it accordingly. Don't worry.
Yeah, your screen is visible, but the PPT yet to be seen.
Right now, you can see. You see, right?
Not yet. Not yet.
Not yet, but
Yeah. Screen is there, but PPT not visible.
not. You can see. I didn't get it. Just hold on a sec. I have to rearrange.
Yes, please.
Hold a second, please. And yes, you can see right now. You have to see.
Yet, not yet.
Not yet. I didn't get why.
Now you can see.
Yeah. Now we see.
Now you can see. Okay then. Okay. All right then. Okay, I'm forwarding. And if you look at the agenda section, I will first define artificial intelligence, which is important topic, as you know. And then we will focus on explainable artificial intelligence. What is it? What is it about? After going over interpretable machine learning techniques, I will present my recently published article. I will also tell you about explainable artificial intelligence survey evaluation mentioned in this article. It's a SCI article. I want to introduce it. And finally, I will make some predictions about the future of explainable artificial intelligence. What is artificial intelligence? It's a very known figure, as you see. Artificial intelligence, machine learning is a subset of artificial intelligence, and deep learning also a subset of artificial intelligence. Artificial intelligence means, AI is a broad branch of computer science with building intelligent machines that can perform tasks typically require human intelligence. For example, AI-enabled computer applications help trained physicians better identify patients who require extra attention and provide personalized protocols for each individual. In addition, the increased use of artificial intelligence in medicine not only reduces manual labor and frees up the trainees' time, but also increases productivity, precision, and efficiency. AI offers enormous potential for industry as well, as you know. It helps companies predict better solutions and decisions through AI-based systems by developing predictive analytics as well as systems ready to make production more efficient, more flexible, and more reliable. And also, similarly, it's used in anomaly detection to find opportunities and vulnerabilities in an organization to develop and protect assets. And part of artificial intelligence is machine learning. As told you before, that machine learning is subset of AI. It's used to understand the data and find patterns. These models can be used to understand different health conditions. An example would be to determine a diagnosis based on the data entered. And typically, machine learning trains AI systems to learn by examining experience with data, recognizing patterns, making recommendations, and adapting. Especially when it comes to deep learning, digital systems learn from examples rather than just responding to rule sets, and then use that information to react, behave, and perform like humans. There are some reasons why deep learning has become more popular. I, I mean, maybe we can say most popular in recent years. First of all, advances in chip technology, uh, for example, NVIDIA chip technology, especially in the field of graphical process units, GPU, allow us to examine larger amounts of data and parallel processing in a very fast time. GPUs are well designed from the matrix maths involved in machine learning. TensorFlow that we're talking about right now. And another important factor is that with the increasing technology, the data sets that were limited in the past, uh, thanks God for social media, because well, all the people almost sharing their pictures and a lot of things in the social media. And as you know, these organizations gathered all the pictures, all the things, especially from social media, and again thanks to spirit of the internet usage. This enables researchers to operate multi-layered structures such as deep learning. This is the most important situation that we have to talk about recently. And shallow architectures such as SVM, support vector machines, single hidden layer, multi-layer perceptron MDP, were used in deep learning, signal processing, and machine learning algorithms. Since some real-world applications, other than the limited and simple problems, have become unsolvable with shallow architectures. As you know, before the deep learning, we have just one or more layers, one or two layers. But real world problems, we cannot solve these layers with these problems. That's why deep learning algorithm has been developed, and these studies have recently begun to affect a wide variety of signal and information processes. It has also developed the scope of problem definitions and solutions, especially in the fields of machine learning. The main purpose of deep learning is both supervised and unsupervised feature selection, and it goes reinforcement learning, this kind of stuff, data transformation, and classification. Higher level and more complex features can be extracted with this hierarchical technique. But the main problem, we are gonna discuss it in a few minutes. You can see how a deep neural network works just by looking inward. I mean, the logic of a network is embedded in the behavior of thousands of entangled neurons stacked and connected in tens or even hundreds of layers. Each of the neurons in the first layer takes an input, such as the voltage of a pixel in an image, and then does a calculation before sending a new signal as output. This output, as you can see, the yellow area, it goes on inward positions when we're not talking about the backward algorithms, back propagation, I mean, and it goes on like that, and general output is produced. But as you know, the hint is when we are dealing with the neurons weights, we have to arrange the neurons weights. We use back propagation algorithm, uh, which change the computations of individual neurons so that a network learns to produce the desired output. Since deep learning is inherently a dark black box, machine learning models designed with millions of artificial neurons with hundreds of layers are not error free like traditional deep learning models. And in that case, explainable AI is very important for us. As you can see, the first thing that artificial intelligence, machine learning, deep learning, it goes like that. But they, it calls they when we're talking about explainable artificial intelligence. They is important part of the artificial intelligence, machine learning, and of course, deep learning algorithms. And that's why we have to think about this figure very important way. With the deep learning algorithm, it has become easier to solve real world problems um, that previously seemed impossible. However, since such complex machine learning models have hitherto been treated as black boxes, we, we are talking so much about black boxes, the human interpretability of intelligent machines often leads to a trade off with model performance. When using simple linear regression models, as we experienced it, multiple linear regression models, simple linear regression models, and other machine learning algorithms that we're talking about, number of parameters makes it possible to explain the decision made. With neural networks, this is much more difficult due to enormous amount of connections. Even a narrow and shallow network can have tens of thousands of connections. The performance and accuracy of deep learning make it attractive to use, but in many cases, the user demands a more transparent system because it matters how and why one makes a decision. If we look at the Google Trends search over the last 5 years for the term explainable AI, the term shows a remarkable resurgence of research interest, as you can see. And as the subject of the machine learning and deep neural networks have become very popular in recent years, the explainability of models continues to be a new challenge for engineers and model stakeholders alike. As you can see, these numbers are increasing day by day. Explainable artificial intelligence, I mean they, is an important field that is not only interacted by engineers but also by people in different fields. They stands at the intersection. We can talk about this stakeholders, human-computer interaction, and user explanation, machine learning, interactive ML, and so on. Model understanding for different stakeholders. As we engineers, at a high level, there are three stakeholders groups of machine learning systems that drive the dual aims of model understanding and providing human interpretable explanations to different stakeholders in order to build trust. The main word is about the is trust. If we can trust the algorithm decision, we stakeholders, consumer regulators or engineers, want to prove that how. Why can I trust the system? For engineers, building models, the focus is more on interpretable machine learning techniques for model understanding and improving model performance. More complex models can be difficult to debug, understand, and control, thereby impeding their adoption. uh, at the engineering parts, uh, we don't tackle with how interpretable is good or not. We don't get involved black boxes or boxes, because we are trusting our codings, and we do whatever we have done at the best point. But uh, when making a decision, when translating these codes to non-engineers, to consumers, to doctors, to physicians, or regulators, doesn't matter at all, we have to explain why this decision is important, because they want see more interpretable models. That's why conversely, trust is the key for model consumers who are looking to understand the impact of model predictions more than the model internals. Interpretable explanations build trust with these end users that the model decisions are reliable, equitable, and can be influenced to achieve better outcomes. And when we skip out the regulators, the role of regulators is to ensure models decisions are in compliance with laws and do not amplify undesirable bias from underlying data sets. Interpretable explanations provide audible metadata to regulators to trace unexpected predictions back to their inputs to inform corrective actions. Now that you have sense of stakeholders' interest and model understanding, let's review some common machine learning workflow tests and how explainability fits in. Understanding models' behavior is critical to many tasks. As part of building and operating machine learning systems. Here are just a few some of my favorite use cases. First, explaining predictions to inform and support human decision making processes. Interpretable explanations build trust with end users that model decisions are equitable and reliable. A second, debugging model performance to inform corrective actions. Interpretable explanations give monitors deeper feature level insight into the cause of model layers. And third, refining modeling and data collection processes. When aggregating and are compared across data set splits, interpretable explanations provide a means to identify and alert on common machine learning pitfalls such as data skew and drift. That is the important ones. And fourth, verifying model behavior is acceptable. And in particular, regulators are increasingly active in validating that machine learning decisions are in compliance with laws and do not result in poor outcomes for model and users. Interpretable explanations provide regulators with means to identify unexpected predictions and inform corrective actions. Lastly, present the model's predictions to stakeholders, which is so important for us. Interpretable explanations are again critical to engineers to build end user trust, and can act as a catalyst to adoption of your machine learning system. Since 2012, the success of deep learning and achieving state-of-the-art performance and even exceeding human-level performance on some individual tasks has come with a trade-off in explainability. This has resulted in some high-profile machine learning deployment failures from these black box models. Many view too opaque, uncontestable, exhibited unreliable behavior, and worse, reinforced undesirable biases that resulted poor outcomes for many stakeholders. In response, since about 2015, the field of ZAI has shifted considerable attention to interpretable machine learning methods to unpack these more complex deep learning models. However, just there is no single machine learning technique. There are many corresponding machine learning interpretability methods to choose from. Let's take a look at some evaluation criteria and taxonomy to assist you in picking the right interpretable machine learning method for your use case. What is your use case and which is about? You have to uh, obey these rules. We have to learn these rules. And interpretive machine learnings, it was two main area, post-hoc and intrinsic. This criteria distinguish whether interpretability is achieved by restricting the complexity of machine learning model known as intrinsic or by applying methods that analyze the model after training known as post-hoc that we are gonna talking about post-hoc models, and the post-hoc models are very popular these days. Um, Interesting interpretability refers to machine learning models that are considered interpretable due to their simple structure. So think decision trees or simple linear regression models, linear models. Post-hoc refers to achieving interpretable after model training. After I mean, you have done classification or segmentation, it doesn't matter at all. We use post-hoc models after training. Permutation feature importance, for example, in one such post-hoc interpretability method. So this is more of considering change in the feature space and how it affects the output of the particular models. Not that post-hoc methods can also be applied to intrinsically interpretable models as well. Local and after training post-hoc models divides the local and global trees, like trees. Local refers to whether the scope of interpretability is limited to individual predictions and or a small part of the model's prediction space. These explanations tend to provide a higher precision view, particularly of individual predictions, but lower recall of understanding of models' behavior across all examples. Global here refers to whether interpretability ability scope is the entire model's prediction space. This is typically accomplished with aggregated ranked contributions of input variables. As a result, these methods provide a more complete map of the prediction space, but can fail to accurately identify certain areas of prediction space and certain individual predictions due to them being obscured by aggregate patterns. This is the main important part for global models. And the entire models and individual predictions devise such branches. Model specific or agnostic. Um, Model specific here refers to interpretability methods being restricted to usage on specific models due to their definition. Examples here include interpretability methods that rely upon some intrinsic part of a model's learning method, such as neural network gradients or three mutual information grade feature importances. Conversely, model agnostic interpretability methods do not rely on model internals, instead relying upon changes and input features or their values to understand how they influence the outputs of your model. Examples here include SHAP and Lime or GradCam or GradCam++. It goes like that. That are portable across different model types, including boosted trees and neural networks. This criteria is more of a fuzzy decision boundary between different methods. Note that you can also aggregate the scores of some local model specific model methods like integrated gradients or sample shuffler to provide global views of the model's prediction space using aggregations like averages and medians. So that we are referring to here is that hybrid bugs on the screen interpretability methods further differ in explanation outputs. These are the theoretical informations about what is they and where it stands in AI, machine learning, and deep learning. Now, for a good example, this SCI article, I want to take a look at this article about diagnosis of tuberculosis in histopathological images, and I'm the corresponding author for this article. Um, eh, I want to introduce this article and how they works in medical sector, research field. GradCam, we used GradCam output. As you can see, this is the original image of the tuberculosis disease. It's a histopathological image. And after deep learning algorithms applied and classified, it's a post-hoc method we used. And then after all, GradCam output, the algorithm is applied, and we have done such a heat map to understand that how can computer sees, and after the sees, how can decide that is the most important question when we are applying the in such algorithms. Let's look at um the search article subject. I have to first introduce the main problem of our article. There are some problems in definite diagnosis of tuberculosis in living animals. The disease can be difficult to detect, especially by inexperienced and young researchers, for the lack of specific findings in the early stage. By the way, I have to say that it's not a medicine, human medicine article. It's about veterinary medicine, and it's definitely detect in cows and other lambs and other kind of animals to provide this tuberculosis disease. And I mean, I don't know you know it or not, but this tuberculosis disease has no vaccine and has no any effective treatment method. That's why it's the most important subjects in veterinary medicine. That's why we, as an engineer, we want to detect and deals with this histopathological analysis uh, to see this cause or another animals have tuberculosis disease or not. And as I've told you before, the black box problem emerging in deep neural networks remains a mystery to those interested in and using artificial intelligence, because physicians and the doctors wants to see, uh, I mean, how to trust your algorithm. You have to prove that algorithm works perfectly. That's why we use they methods, I mean GradCam methods, as you've seen before, for doctors and physicians and other kind of people who are not interested in deep learning or engineers, to prove that these algorithms works really good when we compare young physicians, histopathological people. The physicians and or pathologists need to achieve a moment-to-moment, all-encompassing state of trust cycle. A medical imaging system enables pathologists to examine the work process from multiple points, handle trust relationships actively, and pursue active trust and process evaluation separately. Gigapixel images are more complex than other images when we are talking about histopathological images. It's well known that large-scale histological image features are quite different from ImageNet photos like faces, dog and cat photos, pictures, or radiological images. I don't know, in the audience, you have used your algorithms with histopathological images. It's kind of different and harder than the other kind of images. In this context, this study aims to provide much needed evidence and clarify future research directions concerning the application of deep learning algorithms on histopathological images and the provision of an explainable level of information to pathologists. This is a time consuming, sometimes impossible task. The same happens to veterinary pathologists also. The difficulty of veterinary pathologists in diagnosis can be partly attributed to the fact that very few specialists are experienced in diagnosing the disease of animals with very different physiological and structural feature. Recently, the diagnostic speed and accuracy of both human and veterinary pathologists are significantly improved by the use of AI in pathology. Typically, a deep learning, as you know, technique algorithms consist of thousands, maybe millions, I don't know the problem, real world scenarios, layers of data processing, waiting, and greatly facilitates, classify, and even eliminates human oriented data processing, not like machine learning algorithms. And its accuracy, when we are comparing with performance metrics, when we are talking about deep learning, it's more accurate and more good, better. I mean, when we are comparing machine learning, I mean simple linear regression models or another support vector machines, another machine learning algorithms. The difficulties of applying AI and deep learning to medicine include the missing, noisy, inaccurate, and erroneous datasets of high-dimensional images in medical decision support mechanism. For this reason, researchers are unfortunately deprived of large datasets. To solve the problem, the ultimate solution is to consider the various data on Zaya in the context of medicine. Pathologists must understand how and why an AI algorithm makes a decision, especially on histopathological image. This is the question that we have to when we want uh, prediction accuracy or explainability. It's a trade-off. Okay, I mean, we want if we want the prediction accuracy more than explainability, we use deep learning models, but these deep learning models are black boxes, so we cannot explain the algorithms what is going on over there to stakeholders and other kind of people who are not engineers, especially engineers to engineers cannot explain what it's all about. not fully understand engineers as also, because deep learning has thousands or millions of layers, parameters that are involved, especially when we use backpropagation algorithms. But if you want explainability more important when we are comparing the accuracy performance metrics, we can use machine learning algorithms, but as I've told, is a trade-off. I mean, we have to select which one is more important for us, and that's why um, we have to think about very seriously, critically, uh, uh, our research field. And transparent algorithms like decision trees uh, or support vector meshes show the least performance. Maybe some areas, research areas, not critical areas. I mean, medical sector is a very critical area in every aspect. That's why you cannot compare performance metrics according to explainability. Maybe you know, maybe you don't know. I don't know. Deep learning algorithms is the main part of convolutional neural networks (CNNs), which first introduced by Fukushima, have gained special status as particularly promising form of deep learning. Rooted in image processing, convolutional layers have successfully penetrated almost all subfields of deep learning. As shown in figure, typical CNN encompasses convolutional layers, pooling or subsampling layers, activation functions, connections, and finally RegNet and ResNet, because lack of data. I mean, as you know, deep learning algorithms once not thousands, millions of data when we are talking with deep learning algorithms. But thanks to transfer learning, we can use, uh, I mean, thousands of data. We can use deep learning algorithms, which, if we use transfer learning methods. And in this article, we used VGGNet and ResNet. And also, GradCam is an important labeling tool that can be applied post-hoc, that we have mentioned before, without any intervention in the deep learning algorithm. In other words, the CNN. And the application doesn't need to change the analyzed network. That's the main thing. I mean, first of all, we use transfer learning and we uh, fit the model, deep learning models. We classified at the final part, at the final step, we use GradCam to analyze and to see heat maps about the algorithms. Um, there is the tool emerged as a generalization of class activation. The main difference between GradCam and CAM, uh, class activation, lies in the global average pooling and softmax activation after convolutional layers. GradCam provides significant localization for all cases of image. The localization in an input image are produced by following the gradients in the backpropagation of CNNs. We use the weights. We use weights to heat maps localization. That's why GradCam and GradCam Plus Plus, it goes on like that, is the best algorithm to see this kind of heat maps. Uh, the original dataset was prepared as follows. We didn't download this dataset from any other, I don't know, just hold on a second. I'm so sorry. My phone was ringing. We didn't download the data set. We gathered. This is original data set. We gathered this data set with pathologists in the Department of Pathology, Burdur Mehmet Akif Ersoy University, to understand the importance of tuberculosis. During the necroscopy, blood samples were collected from 20 control sheep and cows and 20 control sheep with natural tuberculosis. Despite the prevalence of tuberculosis around the world, the change in the organism regarding the source of the and development of the disease are not known exactly. Some pathological changes have been recognized as characteristic of tuberculosis, but they are not sufficient for accurate detection of the disease. The commonly adopted manual histopathological analysis is not only laborious and time-consuming, but also limited by the quality of the specimen and the experience of the pathologist. Therefore, this study takes an important step to eliminate the different decisions, both in terms of time between pathologists in the computer environment. Our dataset consists of 520 microscopic images in two classes, disease and healthy. As we skip the performance of models, we scratch, first of all, we use scratch from scratch CNN model. And then we used transfer learning methods like ResNet 50, VGG 60, and we used other transfer learning methods, but their performance metrics cannot good at like this. Therefore, in articles, we showed these three performance of the models. As you can see, the tables 1 to 3, our VGG16 achieved the highest classification accuracy and Matthew correlation coefficient. I mean, I don't know. Have you ever experienced this or I mean heard this performance metric? Uh, our we as an engineers, uh, when we are talking about performance metrics, we generally use a fun score, precision, specificity, sensitivity, and accuracy. This kind of topics, especially we use, but Matthew correlation coefficient is more accurate, more reliable, and trustable performance metric when we compare the other performance metrics. And also we used MCC values in this article. Um, we first of all we analyze when we are looking at these tables which algorithm is the best working for our data sets. And as you can see, VGG16 is more accurate. I mean, accuracy, sensitivity, and others performance metrics, and also MCC value is uh, more important than the others, more higher than the others, and also training time is less than the others. That's why we used VGG system model to generate and to use GradCam method to generate heat maps. And the final output is like that. I'm sorry. The final convolution layers are expected to have the best explanation between high level semantics and detailed spatial information because of the backpropagation and deep learning algorithms layers. In this, in the test images, which were successfully classified with an accuracy 0.98, the region of interest of the VGG16 algorithm were visualized by GradCam. The main purpose here is not just to reveal the outputs of the GradCam algorithm. The level of explainability by pathologists needs to rectify these outputs. That's why a detailed survey of these outcomes was conducted to pathologists. When we analyze these figures, if we look at the right of the figure, this right of the figure, the red areas show us the most relevant locations for classify input picture. And if we look at the right of the figure, uh, there are some in these figures. There are some um, deep crevices. When the pathologist classifies an image, use these crevices. And deep learning, red areas are also focused on these crevices. In this context, we see that deep learning method works best accordingly. And as we mentioned before, we had they survey and asks pathologists it goes perfect or not. When we doing our survey, we used two scales, cover for the scale and the explanation satisfaction scale. The former asks users directly whether they trust the Z system and whether the Z system is predictable, reliable, and efficient. The latter asks users directly whether they trust the Z systems, whether the Z system is predictable, reliable, efficient, and credible. Tables list of questions in CHF scale and Z explanation satisfaction scale, respectively. These questions were asked to expert pathologists. Uh, in the next stage of the survey, a presentation, this is the main important subject for us, a presentation titled What is Artificial Intelligence and How Computers See was given to pathologists to resolve any doubt. First of all, we gave a presentation to doctors what is AI and how computers see. That's the main presentation talk about was about. Afterwards, four visual presentations of tuberculosis disease within the scope of study were presented. Then the pathologists were asked to predict the disease. Since the image of the disease was reflected in the presentation, time was kept with a stopwatch. After a total of 3 minutes 44 seconds, every pathologist wrote the disease in the survey study. In the end, only only three pathologists predict the disease correctly, while seven predict the disease incorrectly or left it blank. That's the saddest moments that I've considered. And these are the surveys, goodness, these are the statistical survey. And when we look at the middle of the table, age, these ages, I mean, the mean of the age 42, work experience 10 years, AI experience. Do you have we asked an AI, do you have an AI experience or worked with study with an engineer or something? Just 2-1 said yes, 8-1 no, and prediction. I mean, we asked the people uh, what is the image about, and just 3-1 said it's tuberculosis, and 7 ones cannot detect the right diagnosis as well. This is very saddest moment. And the result of research, we used original data set. We gathered about tuberculosis disease. You can research or Google up. I don't know Tuberculosis is very important disease in animals. That's why we have to focus on this disease importantly. And when we studied this research with 10 different pathologists. And grid cam was applied to the outputs of the VGG system model, which has the best classification accuracy, as you saw at the tables. The heat maps that created were interpreted by the pathologist as highly accurate, and positive feedbacks were given in terms of performance and ZAE. And in other words, ZAE systems proved as an effective tool in the field of health thanks to its safety for humans and effectiveness. And predictions on the future of ZAE. Now that I've taken to the frontiers of machine learning interpretable methods, I want to conclude this lecture, this seminar, this talk with a few predictions on future directions for explainable AI over the next few years. First, they will become a case standardized component of automated production and pipelines and operational monitoring. Second, model agnostic interpretability methods will continue to be the focus of explainable research. Intrinsic models will certainly still be important, but the focus will really be on model agnostic methods that work across different machine learning techniques. Third, they will converge with causal inference to improve the machine learning reliability and generalization. Fourth, explanations from machine learning interpretability methods will look at uncertainty estimates as a means of further improving human interpretation and also further building trust in when explanations are reliable and when they may not be. And lastly, explainable interfaces will improve the better translate model, understanding to human understanding, and reach more stakeholders. In When we are talking about ZAE models, we are not focusing on just engineers. We are focusing on all the people who are not related with engineering algorithms, deep learning algorithms, or AI. And this might look like more codeless explanation interfaces that are interactive and translate prediction explanations um, to concept expressed in more human interpretable forms such as natural language. Thanks for listening to me. You can Google me. You can see my Google Scholar and other articles. I just showed you one article about the, but I've written in Turkish and English other articles, and I have a book, and it will publish 23 April in a few days later. I will publish my book. I'm the editor of They in Healthcare book. You can download, you can purchase this book uh, as you wish. I mean, uh, so let me.
Thank you
Okay.
very much, Dr.
Thank you
Nilgan.
so much. Or if you have any questions, or you can reach via social media, or I mean, I don't know. You can mail me. It doesn't matter at all. Thank you for listening to me.
Thank you, Dr. Nilgan. Any questions from delegates? If there are any questions, we can ask one or two questions from to Dr.
You can
Nilgan.
ask me, or maybe I can. I don't know. I can share the presentation. You want to share my presentation?
Yeah, share it to my mail ID, Dr.
All
Nilgan.
right, all right, all
Yeah,
right. You can share
yeah,
later,
yeah,
and as I've told you, you can mail me, or I mean, you can reach me via social media, Twitter, or I don't know.
yeah,
You can
definitely.
find me easily.
Yeah, sure, sure. Thank you for the excellent talk. It was very nice to hear. And congratulations for the book to be published, Dr. Nilgan.
Thank you
Thank you
so
very much.
much. Thank you so
Thank you
much.
very much. Thank you very much. Thank you.
Take care
Bye
of
bye.
yourself. Bye
Thank you.
bye.
Thank you. Bye bye. Thank you.
Thank you, madam. Thank you, madam. Very nice presentation.
Yeah.
Thank you so much.
Okay. Okay, madam. Thank you, madam.
Sir, session share joined, sir. Sir,
Yeah. Good evening, sir. Dr.
session, sir.
Shashank Dagadwala.
Sir,
Good
is a
evening, professor.
Karna, sir,
I am
will join
I am
15,
present.
15
I
minutes.
am present.
Yeah,
Sir,
yeah,
I am
yeah.
present.
Yes, sir. Yes, sir. I already saw you. I already saw you, sir.
Okay.
Welcome,
Okay.
sir. Welcome, sir. Welcome.
Thank you, sir. Thank you.
Dr. Balamulidharan, shall we start the technical oral session now?
Yes, sir. Yes, sir. Yes,
Yeah.
sir.
You can please introduce Professor and continue. Let's continue.
Sir, good afternoon, professor.
Good afternoon. Good afternoon.
Okay, sir, head of the department. Gujarat. Sir, please take over this session, sir. Just 5 minutes. It takes a 5 minutes presentation, sir.
Okay.
Okay, sir. Please take over, sir. Please take over this session, sir.
Delegates, kindly type your abstract number for the session. For if whoever is going to present their papers in oral session 2, kindly type your abstract number so that the session chair could call you, invite you, and you can present now.
Abstract number, yes.
Yeah.
20 is there. 20, 23.